Hi, everybody. Welcome to Lecture 3, Magma Oceans, in our Building Planets series. I'm really excited about magma oceans. This is just one of my very favorite topics. So recall where we ended the last discussion. We talked about the first 5 million years after the first solids in the planetary disk, and we discussed 4 steps. We discussed the first solids, those calcium aluminum inclusions, and we discussed how streaming instabilities and Kelvin-Helmholtz turbulence may possibly crush dust and little pieces together to make planetesimals. And we talked about how pebble accretion is the latest hypothesis, a very workable one for how smaller things like pebbles up to, say, house size get slowed down by the gas and pulled in by the gravity of those planetesimals such that planets can be built very fast. And then we talked about how those last really big accretionary impacts create magma oceans. And so today, this is where we're going to start with magma oceans. So here's our timeline for today. The first solids in the solar system, just like usual. Magma oceans on our rocky planets occurred more or less from about 5 million years after the first solids, when big enough bodies had built up to create big enough accretionary impacts that magma oceans would be formed from the energy until maybe 100 million years. And this is really a guess on my part, after which there were not enough big objects left to make magma oceans, maybe magma ponds, but not the whole magma ocean. We don't know for sure when Venus, Mars, Mercury had their last magma oceans. We do know for the Earth, and we'll get to that. And so 100 million years is just a guess. So today we'll follow through what we know about magma oceans, how they're formed, how they solidify, and how a rocky planet starts out. So every rocky planet goes through at least one and probably several stages during their growth when they are largely or completely molten. Now, I'm not talking about that very left-hand picture of the planetesimal that melted from within, from aluminum-26, as we recall from previous lecture. And I'm not talking about those smaller impact-induced magma ponds like on that planetary embryo, maybe something the size of the moon. I'm talking about the one on the right, when the planet is molten all over its surface and possibly all the way down to its center. So this poetic and kind of fantastical step in rocky planet formation really does deserve its own special focus. Why would planets melt? How do we know that they melted? And can we detect any consequences of that melting in today's planets? Well, I would be remiss. I need to remark that the idea of the magma ocean has been around for a few centuries. And Leibniz is the first that I know of who wrote about this. In 1693, in his book, Proto-Gaia, of which this is a handwritten manuscript page, can you believe it? We mostly think of Leibniz as the co-creator with Newton of calculus. But in my opinion, he had a far greater mental creation, which was the magma ocean. He worked as a mining engineer in the silver mines of Germany. And his job was to get the water out of the mines so that mining could proceed. And he used different things. He used windmill-powered pumps, and he used different kinds of pipes with compressed air. He was extremely innovative. And he noticed that when he was down in the mines, it was hot. And when he was up on the surface, it was cooler. And so he did a really fundamental piece of physical little mind experiment. So imagine the Earth is a sphere. It's hotter on the inside. It's colder on the surface. So right away, you've got a time dependency. Heat is passing through the surface and into space and cooling off. That means that in the past, it was hotter because all the time heat has been lost. And he extrapolated back in his mental construct and said, at some point in the very distant past, the planet was molten. And ever since then, it's been losing heat. And I think that's really beautiful that that came all the way back from 1693. So let's talk about how it is possible that accretion can melt planets. We're going to do one simple calculation here, some really beautiful math. Here is a simple and beautiful way to think about whether accreting together a rocky planet releases enough energy to melt the planet and make a magma ocean. This equation is for the gravitational binding energy of an object. Gravitational binding energy. It's the amount of energy needed to stop the planet, in our case, being gravitationally bound together. It's the opposite of the process we're talking about, which is accretion. Rather than how much energy is released when we bring all the parts of a planet together from their original distances where they were not interacting, we ask, how much energy would it take to have the planet we know of and take it apart again and move everything out to the point where it's no longer interacting. And the parts of this equation are the universal gravitational constant, which is an empirical physical constant involved in the calculation of gravitational effects. Empirical meaning it's not derived from theory, it's actually from observations, which is pretty amazing. M is the mass of the planet. I give you as an example Mars. And R is the radius of the planet. And again, an example is Mars. So this is a very simple equation for this. Just how much energy is created when you bring the whole planet together, or how much energy would it take to take it all apart again? And so if you do these calculations for Earth, Mars, and Mercury, you get the following answers. You get about 2 times 10 to the 32nd joules for the Earth, about 1.5 times 10 to the 30th joules for Mercury. Maybe you say, wow, because it's a big exponent, but really we should ask ourselves, what is a joule? The technical definition of a joule is a 2 kilogram mass traveling at 1 meter per second. But maybe in a more relatable way of saying it, it's the energy required to lift a medium-sized tomato up 1 meter. And so 10 to the 32nd of those energies required to lift up a tomato. But I bet we're not any closer in having a gut feeling for whether that's enough to melt a planet. But there's another simple equation, just our second one. This is the change in temperature, delta T, created by an amount of energy, E, divided by the mass of the object that is receiving that energy and the heat capacity of that object. And so the question is, if you have an object of mass M and a certain heat capacity, and you put all this energy into it, how much will its temperature rise? So we take the energy we calculated in the first step, and we get the following answers. For Earth, the change in temperature is about 47,000 Kelvin. And for Mercury, about 6,200. Now, these are the changes in temperature that would be caused by assembling these planets all at once and not letting any heat radiate into space. And so it's a little bit of a simplification, but still many thousands of degrees. Now, taking silicate rock in temperature from the temperature of space up to melting requires a change of about 1,500 degrees. And so all these planets would melt from the heat of accretion. Just accreting a planet is enough to melt it. Now, accretion doesn't happen all at once. And here is a lovely video that was created originally by Casey Liss at Applied Physics Lab to give you a sense of what a giant accretionary impact might look like. And so we've never seen one. What might an impact like this look like? So this is sort of an artist's conception. There was that innocent planet traveling along, and here comes a planetary embryo. It's more or less a Mars-sized object hitting an Earth-sized object. And this is our imagination of what it might look like. Humans have never witnessed an impact like this, and we're still discovering the chemistry and the physics of this unimaginably energetic process. Still, I think it gives us this lovely visceral idea of how the magma ocean is left behind, the heat and the shock of what's happened to this planet. And so let's see, here we go. The last giant accretionary impact that the Earth experienced produced a molten moon and also melted the Earth. In fact, the last giant accretionary impact that the Earth experienced created the moon from the material that was flung out from the giant impact. And that's going to be the topic of a lot of the next lecture. But at the end of this last final giant accretionary impact for the Earth, there was a molten moon and a molten Earth. So the Earth was a huge ball of magma, and the moon was a ball of magma in the sky above. And I love to just think about that. What a crazy solar system we were in at that time. So what was back then? When was this giant impact, which is effectively the age of the Earth? So what is the age of the Earth? Is the age of the Earth 4.567 billion years? No, that's the age of the first solids in the solar system. And so after that came streaming instabilities and planetesimals and impacts and pebble accretion and planetary embryos and more impacts. So then what is the age of the Earth? Well, I would argue that the Earth as we know it started from the last giant accretionary impact, that last magma ocean that reset everything. In 1795, James Hutton, one of the founders of geological sciences as we know it in the West, wrote, we find no vestige of a beginning and no prospect of an end. And he was talking about how all the geological processes that he was able to see on the surface of the Earth were slow and continuous. And if you looked at the evidence from the rock record, they'd obviously been going on for a very long time. And so he began to throw out that idea that maybe the Earth was 5,000 years old. He realized that it was a much longer period of time. Now in 1862, around about different years, Lord Kelvin made several estimates of the age of the Earth between 24 and about 400 million years old. And he was trying to calculate from heat loss how old the Earth must have been. And then a century later, in 1953, Houtermans and Patterson got an age of 4.5 billion years. So what happened in between 1862 and 1953 that completely changed our conception of the age of the Earth? And that was the discovery of radioactivity. This is one of my favorite figures. I've been showing it for years. I think it's so fantastic. It is an X-ray of Lord Kelvin's hand, which seems so ironic because the thing that was missing from his calculation was the natural radioactivity in the Earth. Now we know that maybe a half, we don't actually know the fraction very well, but some large fraction of the heat that is released from the Earth today is from radioactive decay of elements inside the Earth, and not from the primordial accretionary energy that the Earth started with. And so there's a lot more heat than would have been expected just from the accretion of the Earth. So shortly after he made his too small estimates based on too small understanding of heat, radioactivity was discovered. And this image of his hand with its, what I assume is a signet ring on his pinky, was taken at the Royal Society's summer soiree of the 6th of May in 1896. So apparently this is what scientists did for fun in 1896, was they X-rayed each other. And so after the discovery of radioactivity came the concept of a radioactivity clock, which is used, you take the parent radioactive element that is decaying into a daughter element on a known interval. We know what its half-life is. And you can take individual crystals and count the parent element and the daughter element and know the time at which that crystal was created. And so that is the idea of a radioactive clock, and that is what Houtermans and Patterson used on meteorites. But that really, meteorites are not the age of the Earth, are they? They predate the age of the Earth in most cases. So let's think about a more modern way of setting the age of the Earth, that is to say, that last giant impact. Instead of counting back from today or calculating heat loss back from today, let's start at the beginning. Let's start at 4.567 and count forward. So that's how most of the estimates are made now, using a tungsten hafnium radioactivity system counting forward from the beginning, rather than a uranium lead one counting back from today. And so here are three estimates of the time of that last giant impact. Really, it's the time of the last time the Earth's core and its rocky mantle equilibrated with each other. So that's the time of the last impact. The first solids plus 50 million years, the first solids plus 70, the first solids plus 62, with some big error bars on there. And so here's our timeline with the age of the Earth. That is the age of that last giant accretionary impact added in. So you can see on the left 4.5673, the first solids as we've had since the first lecture, and right next to it 4.5, more or less. So 50 to 70 million years after the first solids plus errors is that final giant accretionary impact for the Earth, the moon forming impact. And there you can also see the magma ocean time. Not the time for the Earth's magma ocean. I'll talk about that in a minute, but the period of time in the early solar system where one planet or another was experiencing magma oceans from giant impacts, kind of the epoch of magma oceans. Notice also that I've made some changes in notation. I'm now writing GA, or giga-annum, rather than billions of years, and also MA, mega-annum, in millions of years. All right, so what happened after that giant impact? Well, I've been fascinated by magma oceans for about 25 years now, and I realized fairly early on that a magma ocean is really just a really big magma chamber, in a sense, like what's underneath a volcano. And we know a lot about how magma solidifies. We know it from studying natural rocks and from generations of researchers studying rock melting and magma solidification in the lab. So it's hard to look back in geologic time on Earth far enough to learn about original conditions. Those rocks just don't exist anymore. They've been subducted back into the Earth's interior or weathered away. Instead, I reasoned, we can make forward models from the magma ocean stage and use those models to predict early Earth conditions. The magma ocean is a clean starting point for forward models. So roughly, we think magma oceans work like this. Heat is transferred into space at the top boundary, and cooler plumes of magma, still liquid magma, sink downward into the interior. Those cool plumes start to form crystals as the pressure on them increases in the planetary interior. And so layers of crystals pile up from the bottom, leaving the remaining magma above. So with that basic setup, we can set up a model. So I and a number of other researchers have made computer models of this process to predict how quickly the magma ocean solidifies, what the composition of the resulting planetary mantle is. The mantle is all the rocks between the core and the crust, all that red part once it's solidified, and the composition and mass of the gases that are released into the atmosphere. And you can see here a series of equations that are used to build up these models. It turns out that solidification is rapid, between a few thousands and a million or so years. You can imagine then that over the perhaps 60 million years it took to fully build the Earth, several accretionary impacts were large enough to produce magma oceans, and each magma ocean solidified before the next really big impact occurred. Rocky planets likely have multiple magma oceans before they are fully formed, and there's even compositional evidence in the Earth's mantle that that is true. But wait a minute, are any of you surprised by the idea that an atmosphere is formed over a magma ocean? How could there be gases in a magma ocean? Well, for a long time, people thought that magma oceans were absolutely dry. They could not imagine that any water could stay bound into the magma at the temperatures that we were talking about. It was similarly assumed that the moon itself was absolutely devoid of water. I'll talk about that more in the next lecture. It turns out those are all just misconceptions based on our idea of what it means to be hot here at 1 atmosphere pressure on the surface of the Earth with temperatures that we're used to playing with. And so the material that made up the Earth carried traces of water and carbon and other atmosphere building gases. And when that material melted into the magma ocean, those gases were dissolved into the magma, much as carbon dioxide is dissolved into ginger ale before you open the bottle. And those gases were released into the growing atmosphere as the magma solidified. And then as the planet cooled, here's a really key step, as the planet cooled, that steam atmosphere cooled as well and collapsed into oceans. So how much water was there? This is a graph of the water and carbon content of many kinds of meteorites, some of which might have been left over from the material that built the Earth. On the vertical axis is the water content of those meteorites in weight percent. So a percent of the meteorite by weight, up to 0.7. So 0.7% is as high as this graph goes. And the horizontal axis shows carbon up to 0.4%. But this water was not there as liquid water or as ice. It was bound into rocky minerals. Like you may know the mineral mica. Mica contains water in its crystal structure. It does not seem to be wet. There are water molecules bound in between sandwiches of silicon and oxygen. So similarly for these. Now up in the top right, you'll see a yellow dot that says enstatite chondrites. That is the kind of meteorite, and we mentioned this in a previous lecture, that is the top contender to be what made the Earth. Now, I did models that ran with that amount, the amounts of water in this graph of the magma ocean, and calculated how much steam was released, and then how, if it collapsed back by cooling into an ocean, how deep that ocean would be over the entire surface of the Earth. So you can see a dashed line down low on this graph at 0.1 weight percent, a 5-kilometer deep ocean over the entire Earth would be formed. And at a 0.5 weight percent, a 30-kilometer deep ocean would be formed. So our friend in planetary science, Kevin Zonley, has often said, the problem is not getting water to the Earth, the problem is getting water off of the Earth. We have too much water. And this really seems to be true. So the early sun probably blew a lot of water away from radiation, impacts probably smashed it off, but still this has a very important implication, my favorite implication. These calculations show that it's quite likely that any given rocky planet anywhere in the universe may have started with enough water to have oceans. We already know that virtually every star has planets, and now we know that most every rocky planet probably had some period of time when it was habitable, that is, when it had liquid water. Now here's a little bit of a picture of how the atmosphere of the Earth was built. And so time is along the horizontal axis, and the vertical axis is just a relative amount of gases. And that first red peak is all the gases that are released during magma ocean solidification. And then there's a little bit more with some other lingering magma ocean processes. And then finally in the blue, the convection and volcanism that we experience today continues to drive atmospheric gain. Gases are let out of volcanoes, but it's so small compared to that first magma ocean step. So the Earth's initial conditions are set by magma ocean processes. Magma oceans solidified rapidly, just thousands to million of years. Interestingly, the solid mantle built up in layers was compositionally stable. It wasn't wildly convecting. It was just very stable and quiet, actually, right from the beginning. And there's a deep, dense layer on the Earth today that may have been created by the magma ocean and remain there today down by the core. And finally, a dense atmosphere and water on the surface, all set by magma oceans. And so finally, here's our same timeline with the age of the first solids and our newly defined age of the Earth, that is the moon forming impact, the last giant impact, and final magma ocean on Earth. So giant accretionary impacts create multiple fast freezing magma oceans on rocky planets, which freeze from the bottom and produce a dense atmosphere, implying that rocky planets everywhere may have had liquid surface water for some time and have been habitable. And next time, we'll take up right at 4.5 billion years ago and talk about the formation of Earth's moon.